Hey guys, welcome back. Today we're going to pick up where we left off yesterday. So yesterday we started into the note sheet of 1.5. We talked a little bit about quantum mechanics. We also talked about how electrons, they don't exist in these circular or elliptical paths around the nucleus like we've kind of previously taught you, but instead electrons exist in what are called orbitals. So again, just to refresh, all right, an orbital is a region or a three-dimensional region of space where the electron has a 99% probability of existing. All right, now there's a couple problems obviously, and I did say this yesterday, but I'll say it again. Electrons are moving extremely fast, crazy fast, okay? So because their motion is so fast, it's very difficult to know where an electron is. All right. So as a result of that, we end up with these sort of, just these three-dimensional regions where it exists, and we call those orbitals. All right. So what I'd like you to do is I have five-ish questions here, and this is recapping yesterday. So if you could, please pause the video, think about all five of these, and try to answer them honestly, and see if you can remember what we talked about yesterday. Give these a shot, pause it, and then come on back and I'll give you the answers. Okay, first one. Where do electrons exist in atoms according to the quantum mechanical model? This is orbitals, all right? And again, the name is not great, right? Because it contains the word orbit. It's a horrible name, actually. They really should have picked something different. An orbital, again, is a three-dimensional region of space around the nucleus where these electrons are in, or moving, or exist, okay? Which of these two is an orbital diagram? Keyword there is diagram. That means picture. So I should probably pick the one that has, like, some drawings or a picture, right? It's this guy. All right? The platforms, again, each platform represents one orbital. Each orbital can hold two electrons. And there's arrows. Those arrows, those half arrows, represent electrons. So this is an orbital diagram. How many electrons can any one orbital hold? 2 electrons. That's it. That's all they can hold. Okay? It doesn't matter the shape, and this is where kids get confused. It doesn't matter what that orbital looks like. It can be a sphere. That's an s orbital. It can be kind of like the infinity symbol or a dumbbell, whatever you want to call that. That's a p orbital. Again, different shape. There's 2 regions of that orbital, but it's still just one orbital, so it can only hold 2 electrons. As you get further and further along with d and f orbitals, they get even more complicated, but each orbital can only hold 2 electrons always. How many orbitals are in the p sublevel? If you have a set of p orbitals, let me see if I can move this. Oh, I can. All right, if you have a set of p orbitals, there are 3 orbitals in total in that set. And last but not least, how many orbitals does this picture represent? I have a picture over here off to the right. That looks like a p orbital to me, and I think it's only 1 orbital. So this thing is only 1. And how many electrons could that hold? 2. All right. All right, so for today, we're going to continue forth. I'm going to show you, the next slide is probably the most important slide all week, because it's really going to help you more than, or it's going to help you determine how to figure out the order of these orbitals. All right, so the unique format of the periodic table and the arrangement of the elements will help you learn the order in which we fill electrons in orbitals. Use the periodic table, okay, or we can use the periodic table to determine the most likely place to find a particular electron in an atom. All right, so this is the modified version of the periodic table. All right, normally when you see the periodic table, right, it's this part is taken out below, okay? But if we were really to set up the periodic table appropriately, it would look like this. So each of these sections, and you can kind of see them, right? You'll notice, and I'll use different colors all the way across the way here. There's like a block right here. Okay, that's not the best outline. There's also a block right there. There's a block right here. And then last but not least, there is a block over there, okay? These are representing different types of orbitals. The arrangement of the periodic table, we know that as the numbers get bigger, right, that means that element has more protons. Elements in the same column or in the same family, they have similar properties. We learned that last year too. But these blocks, all right, these blocks aren't random. We don't change to the next row randomly, right? Because if you look at it, it's like, why are there only 2 in the first row? I don't know, that seems odd. Why are there 2 in the first row on the left side, but then another 2 in the second row on the left side, and then another 6 on the second row on the right side? That's kind of weird. Why wouldn't they be like connected or something, right? And so on and so forth. So you see all these breaks, right? We drop down to a new row. Or it's the same row, but we kind of jump all the way across to the other side. The reason why these breaks and these row jumps exist is to explain the orbitals, okay? All of these row changes and breaks in the periodic table are because of the orbital filling of electrons. Let me go further. This block we are going to call the S block. Okay? You can write block if you'd like, but really S is important. All right? All the way across on the other side. This is called the P block. This is called the D block, and this is called the F block. From yesterday, you may remember those are the same letters that represented our orbital types. We have S orbitals, P orbitals, D orbitals, and F orbitals. All right? So think of it like this, okay? We can build an atom, so to speak. All right? Not in a practical sense or not in the real sense, right? We can't just make an atom out of nothing in real life. But on paper or, in our minds or in chemistry, right? We can theoretically or hypothetically build an atom. And as we do so, we would continue to add electrons to the outside of that atom, okay? As you go across the periodic table, element 1, hydrogen, it has 1 electron if it's neutral. And by the way, everything is neutral for today. We're not doing any ions today, okay? So, hydrogen has 1 electron. The 1 electron is represented by the little hydrogen box, all right? So now, again, hang with me for today. This is a little confusing, maybe. But each box on the periodic table no longer represents elements. They're representing electrons, okay? So if I want to add 1 electron and make a hydrogen atom, that electron is in the S block. Okay, there's my 1 electron. I'm going to make a 1 there. If I wanted to add a second electron to make helium, the next element, my second electron is right there. Because these are both in the S block, these electrons, the first 2 electrons, go in an S orbital. More specifically, because this is row 1, these would go in a 1s orbital. Let's keep going. I add a 3rd electron. I add a 4th electron. Those are also in the S block. The 3rd and 4th electrons of an element are in an S orbital, but now it's the 2s orbital, right? So I have 1s, 2 electrons in the 1s, and then the next 2 are in 2s. I keep going. Element number 5, boron, which again is going to be a 5th electron, right? So electron number 5, 6, 7, 8, 9, and 10 all go right here. Again, each box represents an electron. I have 6 electrons. This is the P block. This orbital, where all 6 of these electrons exist, is going to be 2p. So we can keep counting, right? We can keep going. Every electron that we add, if the 11th electron and 12th electron are in this block, they must be entering an s orbital. The 13th through 18th electrons all enter in this block. That's a p orbital. And we can keep on going. So I'll do some more, right? So electron number 11, electron 12, that's going to be a 3s orbital, because again, row 1, 2, 3. Electrons 13 through 18 are in a p orbital. I keep going. Why not? Electron 19, electron 20, that's an s orbital. Ooh, and now we finally hit a different block, right? Electron 21 through 30 are in the d block. Okay, I'm not going to write all the numbers. I think you get the idea. And now this is where it gets a little weird. For S and P, the number out front matches the row. In other words, 1s, 2s, 3s, 4s, right? The row matches. But for D, if you look, okay, and it might be more obvious on your periodic table, this is row 1, 2, 3, 4. So this is actually the fourth row for d orbitals. But when we name it, it gets one less than the row number. All right? It's a little annoying, but that's just the way it is. Essentially, the way that I remember this is that s orbitals first show up in the first row. Okay? The first time a p orbital shows up, it must be in the second energy level. And the first time a d orbital shows up, it must be in the third energy level. And the first time an f orbital shows up, it must be in the fourth. So the first time we see an f orbital, it's actually 4f, even though the 4f electrons are actually in row 6. All right, so I'll talk more about that in the future, but I hope this slide makes sense. This is the big crux of what we're up to today. You got to be able to learn the order of the electrons and the order of the orbitals of an atom. All right, so recap a little bit. I'll go much faster now. That slide was what I really wanted to focus on today. The shape of an s orbital, these are spherical. I don't know how to spell that. If that's not right, it's got to be close. All right, the location on the periodic table, these are the column 1 and 2, right? The first two columns, okay? Number of electrons total per energy level. Well, an s orbital is a set of 1, so there are 2 electrons in an s orbital, all right? P orbitals, these are, I don't know, I'll call it an infinity. Okay, that makes sense to me, like the math symbol, right? Yeah. I don't know. Where are these located? These are columns, really 13 through 18. Depends on the periodic table. Some of these, some periodic tables have this listed as column 3 through 8. Others have it 13 through 18. But it's the last 6, right? The 6 on the right. How many total electrons do they have? 6. A p orbital, or a set of p orbitals, has 3 orbitals, 2 electrons each, so they can hold a total of 6. D orbitals, I don't even know if I want to describe the shape. They're kind of like 4-leaf clovers. Or at least the 4 of them are. The 5th is a weird one, the one in the middle, if you saw the picture, if you go back to the pictures. But anyway, so they're kind of 4-leaf clover shape. And these are the transition metals. That's an E, I swear. The transition metals. So we have 10 columns in the middle of the periodic table that we call the transition metals. That's actually all d orbital electrons, all right? And a set of d orbitals has 5 orbitals. So 5 orbitals, each holds 2 electrons, total of 10. The shape of f orbitals, it's not even worth describing. They're funky. Okay, I'm not even going to write that down. If you'd like to write funky, go for it. But they're very strange. They get very weird. The location on the periodic table, this is the lanthanide and actinide series, okay? That's what they are called. They're named based on the elements that start those rows, lanthanide and actinide. So it's the 2 rows that always get pulled out, right? The 2 rows below the periodic table of how we normally arrange it. F orbitals have 7, or a set of F orbitals is a total of 7 orbitals. Each orbital can hold 2, which means we have a total of 14 electrons. All right, so we're going to jump into, eventually on this sheet, there's a whole bunch of blank boxes kind of, and you can see we're going to be doing orbital diagrams and electron configurations for a whole bunch of different elements, all right? And ions, actually, too. I have a couple ions in there. So let's just run through this really quickly first, and then we'll start doing these practice problems. Number of electrons. For neutral atoms, the number of electrons is the same as the number of protons. I'm going to use P1 plus for a proton. The 1 plus obviously is implying that protons are positively charged. For ions, the number of electrons is different, and again, there can be more electrons or less electrons. We don't change the number of protons, we only change the number of electrons to make an ion. Cations have less electrons than its neutral atom, and ions have more. Again, cations are positively charged, so we've lost electrons. Anions are negatively charged, so we have gained electrons, or there's more. Fill in the orbital diagrams with up and down arrows that represent electrons. Hund's rule says that for orbitals of equal energy, electrons spread out before pairing up. Okay? So if you have a set of 3 p orbitals and you have 3 electrons to add to those p orbitals, you would split them up. Each one of those p orbitals would get 1 electron, and if we had a 4th to add, then that 4th would get paired up with the first one. All right? So electrons that are entering equal energy orbitals always spread out before they pair up. The abbreviated electron configuration is part C. So again, I have A, B, and C on these boxes here. And these are the things I'd like you to do. So I'll do the first one with you, and then I'd like you to give the others a shot. All right? I'd like you to pause it, give them a shot, get as far as you can, and I'll show all these answers, obviously, in just a little bit. But for the first one here, we have carbon. Total number of electrons for a neutral carbon is going to be 6. It's element 6, means 6 protons, 6 electrons. We're good to go. Orbital diagram, this is the arrows. So this is the order of your orbitals, okay? And again, this order is coming off of the periodic table following the blocks, right? So the first 2 electrons, I have 6 to add, right? The first 2 would be element box 1, element box 2. That's a 1s orbital. The next 2 would be element 3, element 4, which are also in the s block, just a row down, so that's 2s. And then my last 2 here are going to enter the 2p orbitals. I have 3 orbitals. They're all the same energy. So I just need to split these up. It doesn't really matter which orbitals they go in. But, you know, reading left to right, that's kind of how I approach it. But anyway, there is your orbital diagram for carbon. Electron configuration, we can abbreviate this, potentially, if you'd like to. Again, the way we abbreviate is you use the previous noble gas from the row above it, and then fill in the rest of the electron configuration after that fact. For carbon, if we were to do this, okay, it would be helium, which is just going to be the first 2 electrons, and then I have 2s2, 2p2. Now, in reality, that abbreviation has quite literally saved me 0 ink and 0 time, because it would otherwise have been 1s2, 2s2, 2p2. So it doesn't really matter in this one, okay? It's kind of a horse apiece. All right, so for the next one, phosphorus, give it a shot, please. Keep going. Don't wait for me. If you want to sit in front of your desk or wherever you are at home or somewhere else, if you want to sit there and work on the next 5 boxes all by yourself for the next 15 minutes and just leave this paused, please do so, okay? I'll go through these answers really quickly when I come back. But yeah, pause it, try these, because I think you got it. I hope you got it. It's not too bad. If you don't know how to abbreviate, that's okay with the electron configuration. You can just write the whole thing out. That's fine too. So pause the video. I'll come back in a little bit. I'll fill in all of these answers. And yeah, we'll call it a day. All right, if you're back, phosphorus. This is element number 15. It's neutral, so that means 15 protons, 15 electrons. I fill these in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, and again, it's important that those p orbital electrons are split up prior to pairing up. Electron configuration. I'm going to use the element neon, which is the noble gas in the row above phosphorus. and then I continue on after that point. So neon has 10 electrons, so all I need is the last 5, which is going to be 3s2, 3p3. If you wrote the whole thing out, it would be that. So really this neon, right, is encompassing that chunk right there. So it saves you a little bit of time, especially as you get further and further along in the periodic table, right? Oxygen. Oxygen is element number 8, neutral, so we have 8 protons, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. I would use helium for my abbreviation, so forget it, I don't need it. 1s2, 2s2, 2p4. There's your oxygen. Chlorine, element 17, a little bigger. This is neutral still, so 17 protons, oops, and 17 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, my drawings aren't the best. I hope yours look a little better. For the electron configuration, again, for the abbreviation, I would use neon, and then I would continue forth, 3s2, 3p5. Without that, 1s2, 2s2, 2p6, 3s2, 3p5. Calcium 2 plus, we have an ion. Okay, calcium, if you find it, is element 20. If it's 2 positive in charge, that means it's lost 2 electrons. So we have a total of 18 electrons to work with. We are all filled up all the way through 3p. Now, I absolutely will not let you do that. That shows me absolutely nothing. Okay? Do I know what that means? Yes, I know what that means. Of course I do. But I don't like it. I'm not going to let you use just a noble gas in brackets as your electron configuration. You got to show me at least something. So instead of writing argon in brackets, if you did that, you can use neon. I'll let you use neon, the one before it. But I need to see something, right? I want to see at least that. Okay? Hydride. Not a hydrogen ion. Hydride. Okay? This is a real thing. It's more rare than a hydrogen ion. Hydrogen ions are everywhere, but hydride's a little weird. So hydrogen normally, if it's neutral, has 1 electron, but it has a 1 minus charge, which means we've gained 1. Okay, we have an extra. There you go. There you go. Boom. Easy peasy. That is all we got for today, guys. I hope this makes sense. Please be aware that the AP Classroom assignment from last Friday, it's 9 multiple choice questions. If you haven't finished that, it is due tonight by 11:45 p.m. So please, if you need help signing in, if you need help with anything with AP Classroom, finding the assignment or something like that, please let me know. I'll try my best to instruct you or help you with that, but that is due tonight by 11:45 since there was a bunch of people missed the opportunity to do that last week. Homework topic 1 was due yesterday. If you didn't get that in yesterday, please turn it in today or as soon as you possibly can. There's a spot on It's Learning to submit it, and all you do is take a picture and submit it. You can do that with your phone or with a Chromebook. And then homework topic 2, HW Unit 1, topic 2, is going to be due tomorrow night by midnight. Okay? So yeah, there's homework to be working on all week long. If you have any questions, please let me know. Pop into my office.